Okay, am I audible?
You are
All
very
right.
much so, yes.
Oh, is it too much?
No, 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 it's very crisp.
All right. Let me just. Okay, is my screen visible?
Yes,
Okay, so hello
very
everyone.
cinematic.
Oh, yes, thank you. Hello everyone. Today, my FOSS talk is going to be on something that I'm personally quite passionate about, which is, well, the universe. Now, I'm in a bit of a tough spot because this FOSS talk will be a bit long, but just bear with me. I'll try my best to not bore you all. So, the universe, simply put, is everything that ever was and ever will be. From the smallest grain of sand to the largest cluster of galaxies to the very existence of space, time, and consciousness. Now, before we delve into some of its intricacies, let me ask you all a question. How did it all start? Well, our story starts a long, long time ago. Roughly 13.7 billion years ago, to be exact. During this time, there existed a fireball, a singularity so small, so hot, that its size cannot be measured. For space and time themselves did not exist yet. This fireball, which was trillions of times hotter than the core of the sun, exploded in an instant. But this was no conventional explosion. For this Big Bang triggered the creation and expansion of space itself. Time, as we know it, began to tick. As the universe entered its first epoch, just 10 raised to minus 43 seconds after the Big Bang, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified as one, and the laws of physics as we know them today simply did not apply. During the second period, from 10 raised to minus 36 to 10 raised to minus 32 seconds, the universe underwent a rapid inflation, expanding by a factor of 10 raised to 78. This expansion is equivalent to a molecule of DNA expanding to the size of the Milky Way. And as the universe continued to cool and expand, elementary particles such as quarks and electrons, as well as their antimatter counterparts, antiquarks and antielectrons, began to form. Now, matter and antimatter, they could not stand each other. They fought a fierce battle, annihilating each other and converting the mass back into energy. If there were equal amounts of matter and antimatter after the Big Bang, the universe would have been left with just energy. However, there was a small imbalance. Maybe for like every billion particles of antimatter, there was a billion and one particle of matter. This meant that after annihilation, a very small excess of matter was left over. And this small excess would form the stars, planets, and everything else that we know of in the current universe. For the next 150 million years, the universe was a bit of a drama queen, cold and dark, with the only light being from the faint afterglow of the Big Bang. Light, which is still detectable today as the cosmic background radiation, permeating each and every corner of the ever expanding universe. Eventually, gravity caused gas clouds to collapse, leading to the formation of the very first stars. Okay, that's enough story time. Now let me talk a bit about stars and why I personally think that they are one of the coolest things in the universe. You see, after the Big Bang, the only elements in the universe were hydrogen and helium. There was nothing else. Now, stars are primarily composed of hydrogen. Now, and since they are so massive, the sheer force of gravity forces nuclei of hydrogen to fuse together in the cores to form helium in a process known as nuclear fusion. The same phenomenon that humanity managed to exploit to create the thermonuclear bomb. Now, the energy released from this fusion is so large that it counteracts the force of gravity. You see, the star is so massive that if it were not for the nuclear fusion occurring in its core, it would collapse into itself. So as a result, the star is in a constant state of equilibrium, balancing between the inward pull of gravity and outward pressure from fusion. But like I said earlier, the star basically burns hydrogen into helium to power its fusion. But what happens if we run out of hydrogen? Well, that's when the fun begins. The star, no longer having enough fuel for fusion, starts to contract, raising the temperature in its core till it reaches about 100 million degrees Kelvin. And at this stage, even helium atoms begin to fuse, forming heavier and heavier elements like carbon and oxygen. And the outer layer of the star expands, engulfing nearby planets. This is precisely what is going to happen to our sun in the next 5 billion years. So,
Just as it fading into the background.
what?
So that's you. That's you.
Oh my bad.
Okay. Yeah, so that's exactly what's going to happen in the next 5 billion years. So, good luck, humanity, assuming we are even around by then. Okay, so we are burning helium now. Now, what happens when we run out of that as well? Well, here is where the story starts to diverge. If the star is not massive enough like our sun, it will simply shed its outer layer and leave behind a tiny little core known as a white dwarf. If you look at the image on the right, you can see that arrow. This arrow points at a white dwarf named Sirius B, whereas the other star in the center is known as Sirius A, which is the brightest star in the night sky. Now don't let its size fool you. Sirius B, the white dwarf, despite being only as large as the Earth, has a mass roughly equal to that of our Sun. And it generates enough gravity to make the other star orbit with itself along their center of mass. Now, on the other hand, if the star is big enough, due to its gravity, the pressure in its core would be so large that it will undergo further fusion. Carbon would burn to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in a day. And then death. Because you see, iron is practically nuclear ash. It is the most stable element, and any further fusion would require more energy than what is released. The tables have turned. As iron, the nuclear ash, builds up in the core, fusion can no longer hold back the force of gravity. In an instant, the star collapses into itself, creating a spectacular explosion called a supernova, which can outshine entire galaxies. The resulting shock wave is so powerful that it spreads gases into a cloud spanning dozens of light years. The ultimate death cry of a dying star. There's not much in the universe that can come close to matching a supernova in terms of destructive potential. It would be like getting hit with a nuclear bomb every second for months. Now remember what I said about hydrogen and helium being the only elements there after the Big Bang? What this means is that every single other element in the universe was created in the cores of stars via fusion. This is also the reason why gold is rarer than iron. Most low mass stars can create iron, but only the conditions leading up to a supernova can create the heavier elements like gold or platinum. So, if you are ever feeling down, just remember that the atoms in your body were created in the exploding hearts of dying stars, sending them on a 13 billion year long journey to create you. You are quite literally stardust. So, stars are pretty cool, right? But let's take a star which is truly massive, around 10 times the mass of our sun. Well, once a star with this much mass reaches the climax of its existence, it doesn't just explode and wither away. No. From the ashes of its spectacular supernova, it will give birth to one of the two most extreme and violent entities known to science: a neutron star or a black hole. A neutron star is a remnant of a supernova which is so dense that a tablespoon of its matter would weigh as much as Mount Everest, roughly 900 billion kilograms. And from the outside, they are even more extreme. Its gravity is the strongest in the universe, second only to black holes. And if they were any more denser, it would become one. Light literally bends around the surface of these stars. The temperatures on their surface can reach as high as a million degrees centigrade as compared to a measly 6,000 on our sun. Their cores are under such immense pressure that we aren't even sure what the properties of matter are under these conditions. Some theorize that the protons and neutrons might dissolve into quarks and gluons, forming a kind of nuclear pasta, which is the actual term, by the way. Like, there's an actual Wikipedia page titled nuclear pasta. Now, and their magnetic fields are so strong. They are not just so strong, they are the strongest in the universe. And they rotate 5 to 10 times per second, sending out pulses that we can detect from the other end of the galaxy. Yes, correct. This is from Kurskasat. Alright. Now, black holes. Honestly, I would have to make an entire new presentation to talk about how absurd these things truly are. But I'll just give a brief overview. When a star of sufficient mass collapses under its own gravity, it shrinks to an impossibly small point, what we call a singularity. Now here is where the absurdity kicks in. This singularity has infinite density but zero volume. Almost an entire star's mass is crammed into a point so small that it does not occupy any space. Their gravity is so strong that even light cannot escape it, which is why black holes are, well, black. In fact, there is actually a point in space around a black hole called a photon sphere where light can actually orbit around the black hole. So if you were to look in any direction when you're at this point, you would just see yourself. Light would travel from the back of your head, orbit around the black hole, and go straight into your eyes. Just imagine how trippy that would feel like. Now, a gravitational field not only warps space, it also warps time. I'm sure most of you have seen the movie Interstellar, which portrays this really well. To an observer watching you jump into a black hole, you would appear in slow motion, maybe even frozen in time. But to you, you would observe the universe around you speed up as years turn into seconds. Basically, a bizarre one-way trip into the future. There's also the information paradox. According to quantum mechanics, information can never truly be destroyed. But when something falls into a black hole, it seems to disappear from the universe entirely. So where does it go? We may never know for sure. The only thing that we do know is that if something managed to escape from inside a black hole, it would create all sorts of time travel paradoxes and issues that could break the universe itself. So in a way, their mystery is kind of essential to the safety of the universe as we understand it. Now, people are often fascinated by science fiction films and short stories that they often forget that the universe that we live in is itself so grand and absurd. One of my favorite things to do, at night, is to just go out, preferably on a day without the moon, and just look up and watch the stars and just wonder about what all is going on out there far beyond our reach. As this photo taken by the Voyager 1 space probe, which I believe has left the solar system by now, shows, we are all just tiny beings on this pale blue dot in this vast cosmic arena. It truly is one of the most humbling experiences, and I would recommend that all of you try it more often. And with that, I would like to conclude my FOSS talk. Thank you.